Welcome to the Deep Dive. Today we're going to unpack something huge. We're looking at the last 15 years of AI, but through the eyes of someone who was, well, literally writing the code for it.
That's right. We're using the work and insights of Jeff Dean, chief scientist at Google DeepMind, leader of the Gemini team, the guy behind MapReduce, Bigtable. The list goes on.
It really does. His career is this perfect bridge from the infrastructure that built the modern internet to the infrastructure that's now building modern AI.
And so our mission today is to really distill what mattered. What were those core breakthroughs in algorithms and just raw architecture that took AI from this, niche academic thing to the force that it is today?
And the speed of it is just, it's breathtaking when you stop and think about it. I mean, 10, maybe 15 years ago, if you said a computer could understand natural speech, really get what's in a photo, or write a coherent essay.
You would have sounded like you were pitching a sci-fi movie. And now that's just standard. It's on your phone.
Exactly. And that capability didn't come from one single eureka moment. It was this convergence of deep learning, a massive increase in scale, and just some really, really clever algorithmic changes.
And crucially, it forced a total pivot in what we even cared about in computing. 15 years ago, it was all about CPU speed. How fast can this one chip do things in a row?
Right, the gigahertz race.
Yeah, that whole thing. Now, nobody cares about that. Now it's all about specialized parallel computations for machine learning. That shift is, it's foundational to this entire story.
Okay, so let's get into it. Let's unpack this journey, starting with the ideas that were, well, they were ancient, but they needed to be scaled up a million times to actually work.
So we have to start with the basics. Neural networks. This idea of artificial neurons with connections that have weights on them. And the network learns by adjusting those weights.
And the mechanism for that is backpropagation, right? Where it learns from its mistakes, basically.
Yeah. Exactly. It gets an error signal and works backward to tweak all the weights. But these ideas, they've been around for decades. The problem was always the brick wall of computation.
And Dean has this fantastic story about that from his college thesis back in 1990. He was trying to do parallel training with, a 32 processor machine?
Right. He was already thinking about what we now call data and model parallelism. But here's the kicker, the part that shows you the miscalculation of the era. He thought 32 times the power was a big deal.
Which it was at the time.
It was. But in reality, to get the kind of performance we have today, he didn't need 32 times the power. He needed 1,000,000 times the power.
1,000,000. The gap between 32 and 1,000,000 is, well, it's everything. It's the whole story.
It's the difference between a cool thesis project and changing the world. And that brings us to around 2012 and the real start of modern scale. The story goes that Dean bumps into Andrew Ng in a Google micro kitchen.
And that's it. That's the start of Google Brain.
That's the genesis moment. Their goal was simple, but completely radical for the time. Just scale up training using as much computation as they could possibly find.
But they didn't have special hardware yet, so they were just using tons of regular CPUs.
Tons of them. And they built this software system they nicknamed Disbelief. And the name is so telling because a lot of experts at the time looked at how it worked and said, that is mathematically wrong. It shouldn't work.
Okay. You have to explain that. How was it wrong? It was doing asynchronous training, right?
Right. So imagine you have, say, 200 copies of your model all training at once. Each one calculates an update, a tiny change to the model's parameters, and sends it to a central server.
Okay.
But it's asynchronous, so by the time your update gets there, the central parameters have already been changed by 10 other copies of the model. You calculated your update based on old information.
So every update is technically incorrect. It's based on a stale version of the model.
Yeah.
In normal computer science, that's a race condition. It's a disaster.
It's a recipe for chaos. But it turned out it worked. Empirically, it just worked. And by doing this messy, wrong thing, they could suddenly train models that were 50 to 100 times bigger than anyone else's.
And that's the lesson, right? That sometimes in this field, sheer scale and data just kind of trumps theoretical purity.
It absolutely does. Which leads directly to the first major success of that scale. The moment they showed you could learn concepts without being taught.
This is the famous cat paper.
The cat paper. So they took the disbelief system and they fed it 10 million random, unlabeled video frames from YouTube. Just raw pixels.
And the only goal was, just to learn how to reconstruct the image?
That's it. Unsupervised learning. Just get good at guessing the pixels. They gave it 0 labels. No, this is a car, this is a tree, nothing.
And the wild part is that it started to organize itself. The model just spontaneously created neurons that were sensitive to high-level ideas.
Not just shapes. It developed a neuron that filed really strongly for images of cats, and another for human faces. It had never been told what a cat was. It figured it out from the raw data.
That's incredible. And that wasn't just a cool party trick. It led to actual benchmark improvements.
A huge one, a 70% relative improvement on the ImageNet benchmark at the time. It proved that this massive, unsupervised pre-training was the secret sauce.
And while this was happening in vision, a similar idea was taking over language with word embeddings, moving beyond just seeing words as, separate tokens.
Yeah, with word embeddings, the model's job was simple. Just predict words that appear near each other in a sentence. And the result was this high-dimensional map, this vector space, where related words,
Like cat, puma, tiger.
they all clustered together. But the truly mind-blowing part was that the directions in that space started to mean something.
This is the king minus man plus woman equals queen example. It still gets me every time.
It's the perfect illustration, isn't it? The model learned this abstract concept of gender as a direction, a mathematical vector, that it could apply to anything. It was learning relationships, not just memorizing locations.
And from there, it's a short step to processing whole sentences, whole sequences of meaning, which gets us to sequence models.
Exactly.
Cool.
Seek. Using things like LSTMs, long short-term memory units, that was the key for tasks like translation. Take an English sentence in, get a French sentence out.
Because the LSTMs had this sort of internal memory, right?
Mm.
To keep track of context over a longer sentence.
Yeah, they had these gates to help them remember what was important from earlier in the sequence. But as the models got better and bigger, that approach started to hit a wall, a very, very expensive wall.
Hardware crisis.
It's the hardware crisis. It was a pure economics problem. Jeff Dean ran the numbers on what it would take to roll out a new, high-quality speech recognition model across all of Google.
And the answer was staggering.
It was that they would have to literally double the number of computers Google owned for one feature. It is impossible.
So they had no choice. They had to build their own hardware, something purpose-built for this kind of math. And that's where the TPU, the tensor processing unit, comes from.
Right. They realized neural nets are mostly just doing tons and tons of matrix multiplications, and they're really tolerant of low-precision math, so you can design a chip that's amazing at that one thing.
And TPU v1 in 2015 was for inference, for running the models. And the speedup wasn't just like 10 or 20%.
Oh, not at all. It was 15 to 30 times faster and 30 to 80 times more energy efficient than the CPUs and GPUs of the time. The paper on it is the most cited paper in the 50-year history of its field. It was that big a deal.
And of course, the focus then shifted from just running models to training them, which led to these TPU supercomputers.
Yeah.
The scale of them is just hard to comprehend.
Well, think about this. The latest generation, called Ironwood, connects over 9,000 chips together in this 3D torus shape, so they can all talk to each other super fast. It has 3,600 times the peak performance of the TPU v2 pod from a few years ago.
Wow.
And it's 30 times more energy efficient. It's this perfect dance, The algorithms demand more scale, so the hardware evolves, which then allows for even bigger algorithmic ideas.
Which brings us to the biggest algorithmic idea of the modern era, the transformer in 2017. This is where we leave those LSTMs behind.
The transformer was a total game changer because of the attention mechanism. Remember how an LSTM tries to cram the meaning of a whole sentence into one little memory vector?
Right. It's like trying to summarize a whole book in one sentence. You're going to lose a lot.
That's a perfect analogy. The transformer's insight was, why summarize? Just keep all the passwords available and let the model learn to pay attention to the specific words that matter most for predicting the next one.
And the results were immediate and dramatic.
Completely. Much higher accuracy with, get this, 10 to 100 times less compute. And the models themselves were often 10 times smaller. It was so effective it jumped from language over to computer vision with vision transformers and gave them the same massive efficiency gains.
So once you have this incredible architecture, the next problem is just making it affordable.
Yeah.
Making these giant models practical, which leads to efficiency tricks, starting with sparsity.
Right. Sparsity is based on a simple observation. When a huge model like Gemini is generating a word, it doesn't use all of its, say, trillion parameters. It only activates a tiny fraction of them.
So you're not firing up the whole brain for every single thought.
Exactly. You're just activating the specialized circuits you need for that specific task. And architecting for that gives you something like an 8x reduction in training costs for the same accuracy. It's fundamental to how today's models are built.
And then there's this really clever idea. Distillation or teacher-steward learning.
Distillation is one of my favorites. You take your giant, super smart teacher model and you use it to train a much smaller, nimbler student model. But the key is how it teaches.
It's not just giving it the right answer. It's not a hard target.
Exactly. A hard target is just the answer is violin. A soft target from the teacher model is a whole probability distribution. It says, I'm 90% sure it's violin, but there's a 9% chance it's piano and a 0.01% chance it's airplane.
So the student learns not just what's right, but what's plausibly wrong. It gets a much richer signal.
A massively richer signal, and the result they found was just astonishing. A student model trained on only 3% of the data, but with these soft targets got to 57% accuracy. The baseline, trained on 100% of the data, got 58.9%.
So you get almost the same performance with like 30 times less data. That's huge for efficiency.
It's how you get these powerful models running on a device in your pocket. But to orchestrate all of this training across thousands of chips, sometimes in different cities, you need a new kind of operating system.
And that's Pathways.
That's Pathways. It's the OS for the AI supercomputer. It manages everything, high-speed networks inside a pod, data center networks, even links between metro areas. It handles chip failures automatically and just presents this illusion of one single giant computer to the researcher. It's a logistical masterpiece.
Okay, so hardware, architecture, efficiency. The last piece is making the models actually smarter, improving their reasoning.
And the first big step there was chain of thought prompting. A really simple but profound idea. If you want a better answer, make the model show its work.
Don't just spit out the final number. Write down the steps you took to get there.
Precisely. And just forcing it to do that led to these huge jumps in accuracy on things like middle school math problems. It forces a kind of internal logical consistency.
And after that initial self-supervised training, you can refine the model even more with reinforcement learning.
Yeah, and we use RL in two main ways. First is for subjective things, like tuning the style to be more polite, or for safety. But the most powerful use is RL in what we call verifiable domains.
Why is that so much more effective?
Because the feedback is perfect. It's not a human saying, I think that's good. If the model generates a mathematical proof, a proof checker can tell you with 100% certainty if it's correct. If it generates code, you know if it compiles and passes the tests.
So there's no ambiguity in the reward signal.
None at all. And that allows the model to explore and learn incredibly complex and correct strategies on its own.
So all of this,
Well,
the hardware, the transformer, the efficiency, the reasoning techniques, it all comes together in the Gemini family of models. What were the big leaps we saw there?
Well, first, it was multimodal from the ground up. It was designed to understand video, audio, text, images, everything, all natively. But the biggest leap, honestly, is in sophisticated reasoning.
I mean, the International Mathematical Olympiad result is just hard to wrap your head around.
It's a stunning jump. A Gemini 2.5 Pro variant solved 5 out of 6 IMO problems. That's a gold medal performance. A couple of years ago, we were excited about basic arithmetic. Now we're talking about reasoning at the level of the most brilliant math students in the world.
And you see this integration in the practical examples, like creating a website.
Yeah, that bilingual recipe example is perfect. It took photos with Korean and English text, translated both, generated images, and wrote the actual website code. It was a complete integrated workflow from a single request.
And then there's that nano banana example, which feels like a window into how it's actually thinking.
That one's amazing. It was a physics problem, and to solve it, the model generated intermediate images. It was running a little mental simulation, a movie in its head of the ball's path, to figure out the final answer.
It's not just using text for its chain of thought. It's using internal visuals.
It's using whatever modality it needs to reason about the world. It's a huge step.
So that brings us to the end of our dive. We've covered this incredible 15-year convergence of hardware, software, architecture, and algorithms.
And the outcome is these incredibly powerful tools with, just immense potential for good in things like science, medicine, education. The main benefit, as Dean puts it, is making deep expertise available to many, many more people.
But we do have to mention the caution, which the sources always bring up. That same power can amplify risks, especially misinformation. And mitigating that is a constant ongoing effort.
Absolutely. But maybe we can leave you with a final thought to chew on. If AI can now win a gold medal in the world's hardest high school math competition and at the same time act as an assistant that can build an entire website from scratch, what area of your own deep specialized expertise is next? What's the next professional barrier that's about to be significantly lowered by AI assistance?